Okay, so good morning to everyone and welcome to our chemistry class. So today what we're going to do is that we are going to discuss about the ligands, okay, the transition metal complexes and ligands. Okay, so we have discussed previously about the properties, physical properties of the transition metals. Okay, now, by the way, for the CA tomorrow, am I right? We're going to have our CA tomorrow. We are going to have, the coverage of the CA will be from the periodicity of period 3, and then until the properties, oxidation, and ligands and complexes of transition metals. Reaction of the transition metals will not be covered by the CA tomorrow. Okay, that will be, but the reactions will be covered in the, it will be included in our BA, but not in the CA tomorrow. Okay, I hope that that's clear. And I have already uploaded all the materials that you need. I have sent the PowerPoint so that you're able to start studying for the CA and also for the BA. Remember that the BA is fast approaching. It will be on the 21st of September. Okay, so I hope that you are preparing for your BA. Okay, so for today, just like what I have said earlier, what we are going to discuss today is about the transition metals complexes. So let's define some terms first before we move on. Okay, let's try to define some terms. Okay, so first let's define what is a ligand. Okay, now a ligand is an atom, or any atom, ion, or molecule which can donate a pair of electrons to a metal ion. Okay, I think you're already familiar with the definition because this is also the definition of the Lewis bases, right? Lewis bases are molecules or ions that can donate a pair of electrons to a metal ion. So that's the same idea of the word ligand. Okay, ligand is any atom, ion, or molecule which can donate a pair of electrons to a metal ion. Now, since okay, it can donate a pair of electrons to a metal ion, then therefore ligands are also called nucleophiles. Okay. What do you mean by the word nucleophile again, Abel? What is a nucleophile? What is a nucleophile? What is a nucleophile? When we say nucleophile, what does it mean?
Donate electron pair.
Donate electron pair. Okay, it says nucleophile or nucleophiles. What this word means? No, you said donate electrons. No, actually, that's not the definition of the word nucleophile. It can donate electron pairs, but that's not the definition of a nucleophile. What is a nucleophile, Leroy?
A nucleus.
Sorry?
A nucleus.
Speak louder, I can't hear you.
A nucleus.
A nucleus. Yaski, can you please help us, enlighten us what the word nucleophile means?
Attract proton.
Okay, attract proton. Okay. Now, where we can find the protons?
In the nucleus.
In the nucleus, right? Okay, now it's a nucleo, from the word nucleus, and phile or phil comes from the word phil, meaning loving. Okay, so in other words, a ligand is a nucleus loving ion, atom, or molecule. Okay, so in other words, you're right. Okay, a ligand attracts nucleus or attracts the proton. Okay, so I hope that you are already familiar with the words that we're using, huh? I believe that you know already what's the meaning of the Lewis base, right? We have discussed this already in the previous class. Okay, so again, no, a ligand is any atom, ion, or molecule which can donate a pair of electrons to a metal ion. Okay, meaning it has a spare pair of electrons. Okay, now what do you call those spare electrons in a molecule? Charlotte, what do you call those spare electrons in a molecule? Charlotte? Allah, Mr. Gideon keeps on asking us. That's a question. What do you call those extra electron pair in a molecule? How do we label them? How do we name them? If an electron is being shared by two atoms, we call that bonding pair. Bonding pair of electrons. How about those extra electrons, electron pairs?
Lone pair.
Oh, yeah, that's right. Very good. We call them the lone pair of electrons. Good job. Okay. Thank you for that answer. Okay, so a ligand can donate the lone pair of electrons to a metal ion. Now, specifically now, here we are discussing about the metal ion. Okay. Now, ligands are classified by the number of dative, covalent, or coordinate bonds. I believe that all of us are already familiar with the word dative, covalent, and coordinate bonds, right? Can you please refresh us? What do we mean by dative, covalent, or coordinate bonds? What are these bonds? Wildy?
Yes, Mister.
What do you mean by the word dative, covalent, or the word coordinate bonds?
Uh, simple covalent bond.
Simple covalent bond that
Supplies one electron to the bond.
sorry,
Supplies one electron to the bond.
okay, supplies only one electron to the bond. That's how we define dative covalent bond.
Yeah.
Okay, Brenda, can you please help us? What is a dative covalent bond or coordinate bond?
The same atom. The bond from the same atom.
The bond between
Electron from the same atom.
okay. When does a dative covalent bond form? When what? Again, Brenda? Okay, can you please just type your answer because I can't hear you clearly? No, we have to clear this up,
In
these
which
terms.
the electron came from.
Okay. the shared electrons come from one atom. Is that what you might want to say? Okay, so when you say dative covalent bond or the coordinate bond, now this is a bond where the electrons that are being shared only comes from the one atom, and the other atom has an empty shell or an empty orbital. Okay, so they share the electrons which come from the one atom. Okay, so that's what you call dative covalent bond. Okay, and we have discussed already when you were in grade 10, and I even asked you to draw the dative covalent bond. How do we draw the dative covalent bond? Nadia.
Yes, sir.
How do we draw the dative covalent bond? How do we draw a dative covalent bond?
Um, like draw there is the from the center and we draw like which one is attached. Give arrow.
With arrow, very good, that's right. So we draw the dative covalent bond using a headed arrow, right? And the
Yes.
arrow is being pointed to the
The element.
the element
That's
that
to the
the atom that
element that
mhm.
shared. It's
Okay,
being shared.
is it the element that has the two lone pair, or rather that has the lone pair of electrons, or the element that doesn't have the lone pair?
That doesn't happen.
Okay, good job. That's right. So when we draw the dative covalent bond, we draw an arrow which is, the head is pointed, okay, to the atom that doesn't have the lone pair. Okay, thank you very much, Nadia. Okay, good job. So water molecules, okay, they are frequently act as ligands. Okay, as you can see, no, okay, there are two lone pairs, okay, for the water molecule. So each water molecule makes a single bond with a metal ion. Okay, ligands, which form single coordinate bonds or single dative covalent bond, okay, they are called unidentate or monodentate. Okay, uni means one, mono means one. Okay, so ligands which form single coordinate bonds, they are called unidentate or monodentate. So in this case, now since water molecule can have or can share one lone pair to a metal, then we can say that water molecule is a unidentate. Okay. Now, this lone pair of electrons on the oxygen can be donated into the partially filled D sublevel of the transition metal. Okay. So again, I remember the transition metal, one of their characteristics is that they have a stable ion when their D sublevel is partially filled up. Remember that property of the transition element. Okay, so for this water molecule, this lone pair of electrons from the oxygen can be donated into the partially filled D sublevel of the transition metal, okay, to form a complex. Okay. Now, when you say bidentate, these are ligands contain two atoms that donate pairs of electrons to form the coordinate bonds. For example, we have ethane 1,2-diamine, or simply we call it N. Okay? Simply we call this N. If you're going to write down the uh, formula, the chemical formula, we use N. Okay, to simplify ethane 1,2-diamine. Okay, so here, as you can see, this is an example of a bidentate ligands. Now, why do you think ethane 1,2-diamine is an example of a bidentate ligand? Funny. Why do you think ethane 1,2-diamine is a bidentate ligand? It has what?
What, Mister?
Look at the structure. Look at the structure of ethane 1,2-diamine. Hmm? Where do you think the coordinate bonds will be formed? Where?
In the middle.
Is it in the middle here? Where do you think the coordinate bonds will be formed? Okay, thank you, Fanny. Let's ask Melly. Melly, are you with us? You see? Is Melly here? Okay, Melly's not around. Okay. Now, Yeski, how about you? Where do you think the ligands will be formed in ethane 1,2-diamine?
Nitrogen.
In the nitrogen, that's right. Because the nitrogen has what?
Pair.
A lone pair. No, each nitrogen has a lone pair of electrons, right? Now, tell me why? Why do you think ethane 1,2-diamine can form two ligands, or it is called bidentate ligands?
It have two lone pair.
Okay, at
It is
its
not
end, okay, it has two lone pairs of electrons, no, that can donate to form
coordinate bond.
coordinate bonds. Good job, that's right. Okay, so both the nitrogen atoms at both ends, no, donate lone pairs to the metal ion. That's why it's called bidentate. Okay, now another example of bidentate ligand is ethane ethane diioate ion. Okay. Now here in this case, the two single bonded oxygen atoms both donate lone pairs to the metal ion. Okay. So this is another example of a bidentate ligand. So for our examples, we have ethane 1,2-diamine, or we just call it N, and then ethane diioate ion, which can donate two lone pairs by the two single bonded oxygen atoms in the molecule. Okay? Okay, I hope that this is clear, huh? And then, if a molecule can donate as many as lone pair electrons as it can, then that is what you call a multi-dentate ligands. Okay? Now, so multi-dentate ligands contain more than two atoms that donate pairs of electrons to form coordinate bonds. Now, here's our example. EDTA. Okay? EDTA ion. Now, the EDTA ion forms 6 coordinate bonds with a metal ion. Okay? So, where are those? So, lone pairs are donated by the 4 negatively charged oxygen atoms Here is 1, 2, 3, and 4. And then the 2 nitrogen atoms. 1, 2. So for EDTA, okay, I just forgot the long name. It's a long name. Actually, we use EDTA for as a medium for bacterial growth. It can also use as a in an assay, microbial assay. Okay, so EDTA. So the EDTA ion forms 6 coordinate bonds, no? 4 from the oxygen and 2 from the nitrogen. Okay, so this is an example of a multidentate ligand. Okay, now let's try to do this one. Bonding atoms in ligands. Now, which is the bonding atom? I would like you to determine which is the bonding atom in this or unidentate ligands. Okay, now we have here the ligands, the unidentate ligands, and here we have their name in complex, meaning the name that is being used in the complex. Okay, if it is water, aqua, ammonia, amine, for the hydroxide is hydroxo, for cyanide, cyano. Okay, but here let's try to identify what are the atoms, okay, that will donate the electrons, the pair of electrons. Let's start with letter A. Let's ask Leroy. What is the bonding atom?
Oxygen.
Okay, it's oxygen. Okay, now let's see. Let's check later. Okay, now Fanny, how about for ammonia? What is the bonding atom? Fanny, what is the bonding atom? Nitrogen or hydrogen?
Hydrogen.
Nitrogen. Okay, now for the hydroxo, let's ask Wildy.
Hydrogen.
Hydrogen, are you sure? Hydrogen has a lone pair of electrons.
No, oxygen.
Oxygen. Okay, now for cyano, let's ask William Ong.
The cyanide.
Yes, which one? Which the bonding atom? Carbon or nitrogen?
The C.
Carbon.
Yeah.
Okay. You're right. Okay, good job. That's right. Okay, so for water, it's the oxygen. For ammonia, for amine, it's nitrogen. For the hydroxyl, it's hydroxide, sorry, is oxygen. And for the cyanide, it's the carbon atom that will give or will donate the electron pair. Now, why not the nitrogen here? In this case, all the nitrogen atoms are bonded with the carbon atoms. Okay? Okay. Now, let's try to identify the ligand. So, what is the ligand type? Now, here, the number of coordinate bonds that a ligand will make can often be predicted by looking at the number of atoms with lone pairs. So, we can identify the number of coordinate bonds that a ligand has if we know how many of the atoms with lone pairs of electrons. Now let's try to study the following ligands and let's decide if they are likely to act as monodentate, bidentate, or multidentate. Okay, let's start. Okay, here. Let's start with Nadia. Is ethane 1,2-diamine a unidentate or bidentate or multidentate?
Bidentate.
Bidentate. Why?
Um,
Nadia? What happened to you?
I forgot to unmute it, sir.
Okay. So why? Why it's bidentate?
Because two, there is two peaks like this. Two lone pair.
Where?
In the uh, NH2 and
Which one? Specifically, which atom?
the nitrogen.
Okay, good job. That's right. Okay, next. Brenda. What is the ligand type?
Multidentate.
Very good. That's right. Obviously, no? 1, 2, 3, 4, 5, 6. Okay, good job. Next. About this one. Let's ask. Okay, this is a methylamine. Let's ask Abel.
Dentate.
Sorry? Again, Abel? One more time?
Uniden.
I think there's something wrong with your connection or with your microphone. It's lagging. It is? Can you just please type your answer? Okay. Are you sure? That is correct. Okay. And the electron pair will be donated by the nitrogen here. Okay. So well done. Good job. Okay. Next. Let's look at the coordination number. Oh, what is the coordination number? Now, the coordination number is the number of coordinate bonds to the metal ion. So it's just simply the number of the dative covalent bond which is attached to the metal ion. Now, this is different, take note of this. This is different to the oxidation state of the metal ion or complex. Now, this is different to the oxidation number of the metal ion, okay, or the whole complex. Coordination number is just the number of the coordinate bonds, okay, which is attached to the metal ion. Okay. Now, let's have this hexa aqua copper. It has a coordination number of 6. Why? Because there are 1, 2, 3, 4, 5, 6. 6 coordinate bonds. That's why its coordination number is 6. Okay? Now, for the tetrachlorocobalt, its coordination number is 4 because we have 1, 2, 3, 4 coordinate bonds. Okay. Now, this is the charge of the complex. Okay. Now, we can say that this is the oxidation state of the complex, but this is not the coordination number. Okay. Now, let's try. Let's try to do this one. Okay. What are complexes? Okay. Now, a complex consists of, take note of this, a central metal ion which is surrounded by ligands, forming coordinate bonds with the ion. Okay? So a complex is just consists of a central metal ion, which is basically a transition metal, and it is surrounded by ligands, okay, forming coordinate bonds with the ion. Okay, let's try to find out more about this term. Okay, ligand. Now here, as you can see, water, this is the molecule. These are the molecules of water, okay, surrounding copper. Okay. Now, water is the most common unidentate ligand. 6 water molecules form single coordinate bonds with the central copper ion. Okay. So I'll show you. Okay. So if you're going to draw the Lewis structure, okay, the Lewis structure of these complex. Now we can see that the copper is the central ion, and copper forms coordinate bonds with molecules of water. Okay. Now when I asked you to draw the structure, make sure that you draw the structure together, or the bond together with the ligand. In this case, it's the oxygen, or the atom that forms the ligand. In this case, it is the oxygen. No, not with hydrogen, huh? Okay, with the oxygen. Now here, if you're going to look at this complex, how many coordinate bonds do you think will be formed? No, you already know it. Okay, there are 6, okay? 6 coordinate bonds. So the lone pair of electrons on each oxygen atom is donated to the central copper ion, forming coordinate bonds. Now, the coordination number is the number of the coordinate bonds. So therefore, the coordination number of this complex is 6. 1, 2, 3, 4, 5, 6. Okay. And then, what do you think is the oxidation number of this complex? Leroy? What is the oxidation number of this complex?
+2.
Okay, very good. The oxidation number refers to the oxidation state of the central metal ion. Okay, and in that case, this is +2. Now, water, as you know, is a molecule. It doesn't have a charge, right? So in this case, this complex has the oxidation number of the metal ion, which is +2, okay, or 2+. Okay. Now, how about this square brackets? Now, the square brackets group together the whole species, making up the complex ion. So when I asked you to draw a complex, you have to draw a bracket also. Do not forget that. And of course, the overall charge, okay, the overall charge of this complex is the sum of the charges on the central metal ion and the ligands. In this case, no, water doesn't have charge. So if you will sum up all the charges, then you will have the charge of the central atom, which is 2+. Okay. Okay. Is there any question? Is there any question? None? None? Okay, let's move on. Okay, let's try to identify the complex ion. Here, which is the transition metal ion? Let's ask William Ong? Which is the transition metal here? Ong? Which is the central metal, the transition
CR.
metal?
This
What is
GR, this
CR?
GR. Chromium.
Chromium. Okay. Next, Galen, the ligand. What is the ligand?
Nitrogen.
Sorry?
Nitrogen.
Nitrogen. Is it nitrogen?
Hydroxide.
Sorry?
Ammonia.
Finally, what is your final answer?
Ammonia.
Ammonia. Okay, next. Leroy, again, the oxidation number.
3+.
Okay, Abel, coordination number.
6.
6. Overall charge. Wildy. Wildy, the overall charge.
+3.
Okay, or 3 plus. Let's check if your answers are correct. Good job. Well done. So this is how we identify, no, the complex ion, no. We have to determine the transition metal, the presence of the ligand, and then also the oxidation number, the coordination number, and the overall charge. Okay? Is there any question? Is there any question?
Sir,
Yes, Brenda.
how to determine the ligand, silicon?
Okay, how do we determine the ligand? I mean,
Yes.
okay, now basically, okay, the common ligands that we have, either ammonia, water, cyanide, and hydroxide. Most of the time, these are the ligands that we have. Okay? So, if you are asked to draw the structure of the complex, okay, now it will be easier for you to determine which, okay? And also, it depends on the name. Remember, when we name the complex, we use, for water, we use aqua. For ammonia, amine. For cyanide is cyano. And for hydroxide is hydroxo. Now, like for example, I will give you a certain complex. Okay. And in the complex, now I just give you the word name. Now, in the word name, there's the word aqua. So I mean to say the ligand is water. Okay? Okay? Did I answer your question?
Yes.
Okay. Is there any other question? If there's none, now let's move on. Okay. Now, there are what you call shapes of complex ions. Now, these are the common shapes: linear, square planar, tetrahedral, and octahedral. Okay. Now, complexes have different shapes depending on the coordination number and the size of their ligands. Okay, let's try to check. Linear. Okay. Now, we have here this structure, no? The silver amine diamine complex. Okay. Now, it's linear. It's linear. Okay. Now, for this complex ion with a coordination number of 2, with a coordination number of 2, meaning there are 2 coordinate bonds, usually Right? Note of this, usually it has a linear shape and the ligands are at an angle of 180 degrees. Okay? So we have dichlorocopper, diamine silver. So those are examples of linear complexes. Okay? Those are the examples of linear complexes. Okay? Remember, if the coordination number is 2, most likely that is a linear complex. Okay? And it has an angle of 180 degrees. Okay? Okay, let's have another one. Square planar. Now, for the square planar, okay, usually it has a coordination number of 4. 1, 2, 3, 4. Okay, now to form the square planar structure. Now, the ligands are in the same plane at 90 degrees to each other. No? 90 degrees here, 90 degrees here, 90 degrees here, 90 degrees here. And they are in the same plane. Okay. Now, cisplatin, this is cisplatin. And we also have the transplatin. Now, cisplatin is a square planar complex. Now, by the way, no, cisplatin, this is used for this complex is used for to cure cancer, yeah, if I'm not mistaken. Okay. Cisplatin. Okay, so this is the structure of cisplatin. Okay, platinum with ammonia and presence of chloride ion. Okay, as the ligands. Okay. Oh, by the way, remember, ligands is either an atom, like the chlorine atom here, an ion, a chloride ion, or a molecule that can give lone pairs of electrons. Okay? So this is an example of square planar. Now let's look at tetrahedral. You're very familiar with tetrahedral, with methane. Now, these complexes with a coordination number of 4 frequently form a tetrahedral shape with the ligands of 109.5 degrees to each other. 109.5, 100.5, 109.5. Now, in this case, we have the tetrachlorochromium. Okay. Tetrachlorochromium. It's tetrahedral. Now, if you're going to look at the square planar, it's made up of 4 ligands also, or rather 4 coordinate bonds. However, they have different ligands. No? But for tetrahedral, mostly, they have the same ligands. Next, we have octahedral. This one. Now, complexes with coordination number of 6 can form an octahedral structure. The ligands are at 90 degrees to each other. And an example of this is the hexaamine chromium. Okay. Now, let's look at this structure. So this is the octahedral shape of hexaamine chromium. Okay. So basically, these are the common shapes of the complexes. We have linear, square planar, tetrahedral, and octahedral. Okay? Okay. And then we also have isomerism in ligands. We know already the stereoisomerism, right? Now, stereoisomerism is where molecules have the same molecular formula, but they have different arrangement of atoms in the space. Okay, now we have the cis-trans isomerism. An example of this is the one that we have seen already, the cisplatin and the transplatin. Okay, now cisplatin is commonly used, it has, okay, oh yes, anti-cancer drug. Now, cisplatin is used as an anti-cancer drug, while transplatin has no medical use. It has no known medical use. Okay, they have the same molecule, molecular, same number of atoms, the same kind of atoms, with the same molecular formula. However, the arrangement of atoms, they are different. They have different. Okay, so this is an example of cis-trans isomerism. Okay. Now, another isomerism that you're already familiar with is optical isomerism. Optical isomerism is the mirror image. Okay, you cannot superimpose them. Okay. Now, here we have our example. We have the hexaamine nickel complex. Okay, it forms an optical isomerism. Okay, any question? Do you have any question? Do you have any question? None? Okay, now for this time, at this time, I want you to go to, I'm going to group you into groups. Okay. Now, in our GC, I have posted there worksheets to answer. You have to work with your group mates. Okay. You have to work with your group mates. Now, after you are done, you just post your answer in our GC. Each one of you should have a copy of your answer. Now, here, I want you to work with your classmates. Now, at this time, I want you to help each other, but it doesn't mean that you will let your classmates just to copy from you. No, I want you to work with your partner. I'm going to group you into 5 groups, so you will have a partner. Okay, you will be grouped in pairs. Okay, so do you have any question before I send you to your breakout rooms, to your pairs? Is there any question? None? Now, I would like you to refer from your textbook. Okay, use your textbook as your reference and the PowerPoint that I have sent in your GC, in our GC. Okay, do you have any question? None? No question? Ready? Ready to the group? Okay, now if you're done, you just leave the room. Okay? Okay? You don't have to come back to our main room. Okay? If there are no questions, then get ready. So I have already grouped you into pairs. Okay?